Hi. So today I want to talk about the Pisano period. And I really should get like a whiteboard. But if you know the Fibonacci sequence, that's gonna help here. So, start with like a 1 and then a 1. I think I have it over here because I was explaining it to my friend. It starts with 1 and then you have another 1. Yeah, here we go. Pisano period. Well, so we're going to talk about Fibonacci sequence real quick for those who don't know about it. And this all relates to the golden ratio stuff too. You heard about that stuff? That stuff is cool, man. This is like really cool math, okay? Yeah. And so, let's see if I can get this in here. So starting with 0 there, optional. So the first two numbers are given, okay? So 1 and 1, those are the first two numbers. Then you just add them together, okay? And so you get 2. And then you add the previous two terms. So 2 plus 1, and you get 3. Then you add previous two terms, 3 and 2, and you get 5. And then you do it again, you get 8, and so on. Okie dokie. And so that's the Fibonacci sequence, okay? So Fibonacci wrote this down like almost 1,000 years ago. Like I used to think it was like in the 1500s or something, because that's when there's like the Enlightenment and all this kind of stuff, the early Renaissance and stuff. But no, it was like almost 1,000 years ago. It was longer ago. And but actually Fibonacci, apparently this sequence is written in like old Sanskrit stuff, so it's really kind of ancient. And sometimes I like to think of it as starting with 0, okay? So we start, instead, this is the 0th number in the sequence, and this is the first. And then we add 0 and 1, and we get 1, and we continue like that. For me, because some people will feel like if you start with 1 and then 1, it feels a little more arbitrary. But I think starting with 0 and 1 sort of reveals that this is like really, canonical, and it's like this God-given sequence. It's special, okay? Because 0 and 1 are special numbers. Anyway, or if you started with 1 and 2, you could start with 1 and 2, and those seem like, obvious numbers to choose, because that's like counting. But if you start with 1 and 2, then, you start with 1 and 2, and then the next number is 3, and then the next number is 5, and it continues like that. So you'll get that. If you start with 1 and 2, you're just starting the Fibonacci sequence later. Now, you can generalize the Fibonacci sequence with different starting values, okay? And that is interesting. That will be called, if you want to search for information about that, we call those binary linear recurrence sequences, I think. A little fancy names, mathematicians, they like their fancy names. Binary linear recurrence sequence, I think. You'll find that kind of stuff. Crap, what else was I going to talk about? Pisano periods, we could talk about that. That is where you do the Fibonacci sequence mod a number. There's another thing I need to talk about at some point, which is there's a related sequence called the Lucas sequence, Lucas. Some people refer to it as Lucas or Lucas numbers. The guy was French, so I'm pretty sure it's pronounced Lucas, but whatever, doesn't really matter too much. There's deep stuff going on that I think we don't quite understand. And if you think I'm being, a little bit dramatic or hyperbolic here, well, the other thing that I'm going to talk about, which is the Pisano period, is a very simple concept. And we do not have a general formula for the Pisano period of a number, of a whole number. And so that is my evidence. I think that's strong evidence that there's things going on here that we don't understand yet. Now with the Fibonacci and the Lucas sequence, they have some almost like some kind of mystical relationship. There are ways in which you can sort of create this sort of context where Fibonacci is sort of acting like cosine and the Lucas sequence is sort of acting like sine. Michael Penn has done a video on that on YouTube if you want to check it out. And but anyway, so there's a lot of deep sort of mystical seeming things. Now, should I talk about the golden ratio? I could explain how the Fibonacci sequence is connected with the golden ratio. I think though all of these binary linear recurrence sequences are often connected to the golden ratio. But anyway, let's talk about the Pisano period because I haven't talked about that. So I'm going to quickly explain what mod a number is. If you do modulo a number, basically, where do I have that written? I'm looking at this and it's mirrored, so I have trouble seeing it. So if we're doing mod 3, if we count in mod 3, we start out normal 1 and then 2, but then 0. So it's like a clock. So we all know a little bit of how this mod thing works because we understand the clock. The clock works mod 12. So on the clock, if you have 11 and you add 3 to it, you get 2. You don't get 14, you get 2. That's basically what modulo means. It's basically, so if you add 11 plus 3 and you get 14 and it's mod 12, that means, or modulo 12, that means you take away 12 in that case. But it's basically, you have, if you give me some number like 49, what is 49 mod 12? What I'll do is I'll divide by 12 and then I'll take the remainder. So if you give me 49, how many times does 12 go into it? 4 times, so because 4 times 12 is 48. So I sort of remove that part and I'm left with the remainder of 1, and that's my answer. So 49 mod 12 is 1. All right, so that's how modulo works. And so you can do modular arithmetic. You can add things or multiply them and then do it mod some number. This is kind of related to bases, right? Because if you're working in base 10, like normal numbers like we do, and say you look at the first digit, that is basically the number mod 10. And if you're looking at the first 2 digits, that is going to be your number mod 100, because if you give me some long big number and I only look at the first 2 digits, that's the same as taking mod 100. So there is a connection there with bases in general, and modulo stuff is really important for programming, really valuable. And so the Pisano period, so what we do is we just do the Fibonacci sequence mod a number. So if we're doing mod 3, I like to start with 0 as the 0th number. That's just a personal preference. But anyway, so, and then 1 is the next one. So that's just given, okay? Well, we add those together, we get 1. We add those together, we get 2. When we add 1 plus 2, mod 3, we get 0, okay? It's just like how 12 o'clock is the same as 0 o'clock. I don't think you say 0 o'clock in English, but actually in Japanese, they say 0 o'clock in Japanese, so why not? So then, yeah, 2 plus 1 mod 3 is going to be 0. And then 2 plus 0 is just 2. And then 0 plus 2 is 2. And then 2 plus 2 is 4, which mod 3 is 1. If that doesn't make sense, then review what I just said about, when I just explained mod, review that again. But 2 plus 2, mod 3 is 1. Then 2 plus 1 is going to be 0. Oh, I wrote it down here, back down there. So 2 plus 1 is going to be 0. And then 0 plus 1 is going to be 1. So here, at the bottom here, where my ring finger is pointing to, now we're repeating. Okay, eventually this has to repeat. because there's only so many numbers if you're working modulo. I mean, if you're not working with some kind of modulo, the Fibonacci sequence will keep getting bigger and bigger. It's never going to repeat. But because you pick some modulo, let's say you pick 256, mod 256, there's only so many numbers there. There's, well, there would be 257 numbers because you have from 0 to 256. That's 257 different numbers. And so you have a number and then you have the next number. Once it repeats two numbers in a row, that like you have two numbers in the sequence and it's done that in the past already, then it's just going to keep repeating because of, I mean, it's not that hard to see because with the Fibonacci sequence, we call this I think we call it the fundamental Fibonacci relation, that, you know, the way you calculate a number is to take the previous two numbers and add them, right? We call that, I think we call that the fundamental Fibonacci relation. And if you think about that a little bit, you'll realize that eventually it has to repeat. And in fact, the maximum possible digits until, or numbers until it will repeat itself is going to be n squared, because you have you think of it as pairs of numbers, and there's, if we're doing mod 256, then n we'll say is actually 257. Is that right? Maybe that's right. I think I might be off by one here for some reason. But anyway, let's say 257 is n. So we have 257 possibilities for the first one. No, because 256, actually achieving 256 is the same as 0. So there's actually, so I actually messed that up earlier. There's not 257 possibilities, there's 256. And so there's 256 possibilities for the first number, and then for the second number, so that's just going to be 256 times 256 possibilities, which is n squared here. So anyway, that's not too important, but there's an upper bound here. But we don't have the general formula for how to calculate the, this is called the Pisano period. It's how long this sequence goes until it repeats. Okay, so the Pisano period is how long, so the Pisano period of a number is how long the Fibonacci sequence goes, mod that number until it repeats. So the Pisano period of 3, I just showed you, is 8, because it goes 0, 1, 1, 2, 0, 2, 2, 1, and then it repeats. And so that is 8 numbers before it repeats. So that the Pisano period of 3 is 8. So we just calculated that. So, but what we want is a formula. You give me a number, you give me some big number, 1,337 or something, and I just have a formula, and I tell you this is going to be the Pisano period of that number. That's what we would like to have. Now that said, so we don't have the general formula, but we do know a lot of things. And so I'll kind of briefly go over that. Basically, if you know, let's say you know the Pisano periods of two primes. So let's say 3 and 5. So for 3, we just calculated it, it's 8. For the Pisano period of 5, maybe as an exercise, calculate that for yourself, but it's 20. And actually 20 is quite large for a Pisano period, relative to the number. But anyway, so there's a theorem, and I believe it's proven, that if you then were to take, say, the Pisano period of 15, so that's 3 times 5, then all you do is you look at the Pisano periods for the prime numbers, and you take I believe you take the lowest common multiple of those two numbers. So in this case, the Pisano periods were 8 and 20. So what's the, so I guess the LCM, the lowest common multiple, would be 40. So I think that would indicate that the Pisano period of 15 should be 40, if I'm not making a mistake. So we know that, I believe we know that, and then there's something called Wall's conjecture, which I won't explain here. If I had a whiteboard, maybe I'd explain it. It's not that complicated, but the spark notes here, getting to the core of it. I think anybody who studies this problem probably concludes fairly quickly that it's the real question here is just figuring out. We want to figure out the Pisano periods of the prime numbers. Once you figure it out, if you have an equation that figures it out for the prime numbers based on this LCM thing that I was just explaining, we have it for all the numbers. Okay, so there's that. And then Wall's conjecture specifically has to do with it's the relationship between the Pisano period of a prime P and the Pisano period of a prime squared, of that same prime squared. So it's the Pisano period it's a relationship of the Pisano period between P and P squared, where P is a prime. And so there's a conjecture there, and that's interesting stuff. I'll talk about that another day. But anyway, so I'm interested in proving or disproving Wall's conjecture, which has been an open problem since 1960. That's when Wall's conjecture was made. And then there's the more general problem of the general formula for the Pisano period. So these are open problems that I've been working on since early May, maybe like a few hours every day in the morning kind of thing. This is just where I'm at with my my studies, because I've been studying physics and math, I guess, for a while as a hobby. And this is just what I've arrived at. Yeah, so that's the Pisano period. I think it's quite interesting. You can play around with things. And you know what, there's some other stuff where there's something that's sort of like a Fibonacci base. So if you've never done this, I think you should study different bases. So if you're a programmer, you've probably studied, you study binary, which is base 2. You study hexadecimal, which is base 16. The number system the whole world uses is base 10, okay? So that's why when you count, you could start at 0 and then get to 9, and then after 9 is something special happens. You write a 1 and a 0, right? So that's because we work base 10, and then all of the places are powers of 10, right? You have the tens place and the hundreds place and the thousands place and so on. And even the ones place that's 10 to the 0th power. And then you have the 1/10th place and the 1/100th place and so on. And those are negative powers of 10. So you can easily, do a different base. And I think most people do not really study this in their, what do you call it? Primary, middle school and high school. What is all that called? We call that K through 12 in America. K for kindergarten, 12 is 12th grade, so say K through 12. But can you call it primary education? I don't think so. I think primary education is just elementary school. Anyway, I feel like most people don't study different bases. Some people do. There was a Simpsons joke about this in The Simpsons, but anyway. I actually tutored math one time for somebody who was studying to become a teacher, and they had to learn how to do some arithmetic in different bases. And the teacher, the aspiring teacher that I was tutoring, thought, like, what is the point of this? We're never going to use this. It's totally useless. We're not even going to teach this. I disagreed. I thought, no, this is important, because one day you might get a student who is curious about, who notices, oh, we're using base 10, and what about other bases? They might ask you about this. And if you weren't being educated about this in college in preparation for being a teacher, then unfortunately you might say something silly or wrong to the student. But because you're learning this, then it's educating you, it's giving you some knowledge so that you could at least inform the student, hopefully in a good way, and maybe either explain things to them or point them in some direction where they can learn more. Now, you can't, so an interesting thing is you don't just have to choose whole numbers for your base. There's nothing stopping you from choosing irrational bases. You could choose pi, base square root of 2. Now, if you know the golden ratio, it's actually kind of interesting if you do base golden ratio, because with the golden ratio, there's some special properties. If you don't know what the golden ratio is, I'm not going to explain it. I have previous videos. There's videos all over the internet. It's an irrational number. It's special for various reasons. There's a lot of nonsense out there on the internet about the golden ratio, but just forget about that. So be a little careful as you're learning about it. But so it has some special properties, and actually in base golden ratio, you can write finite numbers which are integers. So that's a little interesting because the base itself is irrational. So for example, 10.1, okay? 10.1 in base golden ratio, would, I believe that it just equals, oh no, sorry, it's a little more complicated than that. But anyway, the fact remains that you can, it's sort of interesting because you can get whole numbers in an interesting way using base golden ratio. Is there something more I want to say there? I guess I could make another video about that topic specifically. It's sort of interesting. But anyway, so there's this thing that you could kind of consider to be sort of a base Fibonacci, but it's technically you have to, I think it's technically not a base, but basically, you know, when you have some base, you have, let's say in decimal, you have, or base 10, that's decimal, you have the ones place, the tens place, the hundreds place, and so on. If you're working in base 5, you'd have the ones place, the fives place, the 25s place, the 125s place, all that stuff, right? Powers of 5. So in the Fibonacci representation, it's actually called the Zeckendorf representation. It's named after someone who wrote a paper about it. But I'll just call it the Fibonacci representation. Those digits correspond to Fibonacci numbers. So you do have, and we don't need to count 1 twice. 1 appears twice in the Fibonacci sequence, but we only need one. So we have the ones place, then we have the twos place, the threes place, the fives place, the eights place, the 13th place, the 21s place, and the 34s place, and so on. And so what's interesting here is you could, and by the way, you can go in the opposite direction here. You can calculate this way. If you put a -1 here, then -1 plus 0 is 1. Sorry. No, you put a 1 here. 1 plus 0 is 1. And then over here, a -1. -1 plus 1 is 0. So you can have, so this is 0 here is the 0th Fibonacci number. You can have Fibonacci numbers with negative index going the other way. And using all of those, you could then represent, I believe you can represent any integer using that whole system. I tend to just focus on positive numbers, positive integers. So you can represent any positive integer in this Fibonacci representation, Zeckendorf representation. Now what you'll notice if you play around with this a bit, you'll notice fairly quickly that if you, so you write out you can write out numbers like, it'll just be ones and zeros, okay? So I work in various bases, so just ignore, I don't remember what this is, but you've got a bunch of ones and zeros. I was probably adding these numbers together. But anyway, yeah, all you need is ones and zeros here. And then what you'll notice is that when you have consecutive ones, the thing is that all of these digits, you get the next digit by adding the previous 2 digits because it's based on the Fibonacci sequence. So we had a 3's digit and a 5's digit, and the next digit is going to be 8 because that's 3 plus 5, right? So if I had 2 consecutive 1s in my number, so if I had a 1 in the 3's place and I had a 1 in the 5's place, you can add them together to get a 1 in the 8's place, and just, so they sort of, when you have 2 consecutive 1s in this representation, they just sort of push forward. Okay, am I doing this the right way? No, this way. When you have 2 consecutive 1s, they just sort of push forward. And so if you accept that rule that so I believe the Zeckendorf representation, if I'm not mistaken, sort of has this rule that you represent the positive whole number, the positive integer, with a without any consecutive 1s, okay? Because it can always be sort of pushed forward. And I believe that's the Zeckendorf representation. I might be making a little mistake there, one of the details or something. But so that's sort of interesting. So I guess the Fibonacci sequence is special in all of this because you can choose other starting values, right? For example, in the Lucas sequence, it doesn't start 1, 1. It starts 2, 1. So it's 2, 1, and then 3, and then 4, 7, 11, 18, 29, ... And so those are different binary linear recurrence sequences. And but I guess only the Fibonacci sequence has this where all the whole numbers can be sort of have a canonical representation, just one way to be represented, assuming this this thing where you don't have consecutive 1s involved. So I'm just trying to say that somewhere in this general study of this stuff, the Fibonacci sequence in particular is special among these binary recurrence relations, probably in many ways, but that is one way in which it's important, because what that means is that you can use this Fibonacci representation, which I guess a quicker way to explain that, I just explained it a certain way, but a quicker way is that every integer is a sum of Fibonacci numbers with without any consecutive indices in the Fibonacci numbers. Now that's a bit more of a mouthful, and I think if I just said that, it would be hard, like very few people would understand that right away. So, but I'm saying that now that I've explained it in more detail, in a more easier way, maybe you can understand this more brief explanation. It's any integer can be represented as a sum of Fibonacci numbers where none of them have consecutive indices. When I say none of them have consecutive indices, that means that we're not using the consecutive 1s in the representation, because the consecutive 1s can always be pushed forward. Sorry, I know it's confusing. But if you watch this a few times and give me lots of watch time and smash that like button, then I think you'll understand what I'm saying. So, but what that means is that this is a way of representing integers. So, I mean, integers, whole numbers, etc., are rather important in math. They come up a lot. They are numbers, and the fact that you can sort of have this Fibonacci representation, Zeckendorf representation if you prefer, is interesting. And certain things, maybe there are certain things out there where if you translated everything into this Fibonacci representation, maybe certain patterns would become more obvious in certain cases. So one thing that you can do, and then there's a similar, I tried to you can kind of make a Lucas representation as well, but there's a couple maybe like sort of thorny issues with it, and it's yeah. For example, I mean, a lot of the numbers do not have unique representations. I kind of talked about that earlier. So for people who are into math, it's maybe slightly annoying that you can write the same number multiple different ways. Now, I think it would be interesting to study these various binary recurrence sequences and sort of make a study. I'm sure people have done this, but sort of make a study of, first of all, a lot of them you won't be able to represent all the integers or all the whole numbers. A lot of them will have gaps, but those gaps sort of, how to explain it? When I think of the Fibonacci sequence, I sort of imagine something being rolled up, like a carpet. Imagine somebody's rolling up a carpet, and you can see it from the side, so you're seeing like a cross section. I guess that sort of corresponds, like with the Fibonacci sequence, people often represent it with spirals, right? It's kind of the same thing. But the reason I imagine it as sort of a carpet rolling up is because, like, you can take like 34, for example. Well, you can sort of decompose that into 21 plus 13. But then, okay, well, 13 you could further decompose into 8 and 5. Or alternatively, you could decompose the 21 into 13 and 8. And so given 34 here, which is the 9th Fibonacci number, you can make up a bunch of relations where you decompose it different ways. It's almost like a little, you almost have like a little pyramid of different options of ways that you can decompose it into previous, sums of previous Fibonacci numbers. And in fact, there's deep connections between the Fibonacci sequence and the Pascal's triangle. So that's kind of what I'm saying here about this pyramid thing. And I mean, you can look that up. There's lots of papers. There's blog posts. There's videos. I think there's some somewhat straightforward connections with Pascal's triangle and the Fibonacci sequence. I think there's also deeper connections. There's obvious things, and I think there's deeper connections there as well. But yeah, so I sort of imagine, when I think of the Fibonacci sequence, I imagine this sort of carpet being rolled up kind of image. I forget why I was saying that. Okay, so if you study different binary recurrence sequences, then it's sort of like as this carpet is being rolled up, there's sort of gaps that keep, like there's like, imagine like a sort of a triangular gap that sticks out. And as the carpet's being rolled up, there continues to be this sort of gap spinning around. Or if you're thinking of a spiral, there's going to be sort of gaps that sort of spiral out. Okay, that's how I imagine it anyway. So that could be interesting to study. I'm sure it's been studied. And then also look at sort of so with the Fibonacci sequence, you have this canonical representation, the Zeckendorf representation, where every integer is uniquely represented. But then, for example, in the Lucas sequence, or if you try to make something like a Lucas base or a Lucas representation, and I've seen that kind of stuff in the literature a bit, then you're forced to allow, well, I think you're basically forced to accept that certain integers or whole numbers are going to have more than one possible representation. So that if you try to do something like a Lucas base or a Lucas representation, analogous to what I just said about Fibonacci representation or Zeckendorf representation, if you try to do that, you'll run into a couple of thorny issues. Now, I haven't actually really checked the literature. I think there was one paper about this that I couldn't find. Actually, Zeckendorf's paper was in French, I believe, and I can't find it online. Now, I can read French, so a translation or the original paper would be fine. So I think I have to go physically to a library to find it. Anyway, and that I believe also discusses sort of Lucas representations of whole numbers or integers, I believe. I believe it's in the title. So anyway, yeah. So I actually recorded a video where this was a couple months ago, I was talking about these representations, and also there's the Fibonacci base, the golden ratio base, which is also called Phinary, P-H-I-N-A-R-Y, which is interesting. Now, I recorded this video and I didn't release it. I really sort of stumbled over it. I was in the process of figuring out some of the details, and I had been so down in the weeds that I had forgotten, like it was difficult for me to explain, like from the top down. There were still certain misconceptions. I was a little confused on certain things. So I didn't publish that. However, I might publish it because that's when I realized in real time how I wanted to, at least for myself, my preferred way to do what I'll call the Lucas representation. Because I think if you set certain ground rules, you then need additional rules to make the representation unique in the Lucas sequence or the Lucas representation. With the Fibonacci representation, you just need the rule that if there's two consecutive ones, that you sort of pass them forward. That's enough to give you a unique representation. With the Lucas representation, you're going to need maybe one additional rule. But because of these thorny issues with the Lucas representation, I was sort of having some trouble, and I kind of did it in real time, and recording that video actually really helped me to organize my thoughts. So I might publish that. So if you're listening and you want to see it, leave a comment. Maybe I'll publish it. Maybe I'll publish it tomorrow. I don't know. But anyway, so an interesting thing to do is, it's an interesting exercise. For example, do the Lucas sequence in the Fibonacci representation. In fact, I think I have that, sort of have that here. So I write these, it sort of looks like a pyramid, right? I'm writing these numbers. So let's start at the top here. So we have this 101. So what am I doing there? So this is slightly different. This is my Lucas representation before I had really figured it out. What I'm doing here, let's forget about the top two numbers. This one here is actually corresponds to the number 2, because in the Lucas sequence begins with a 2. So an ordinary 1 in the Lucas representation is a 2. So 1, 0 is the number 1 in the Lucas representation. I'm calling it the Lucas representation. I don't know. I don't think that's standard nomenclature. I don't think it's standard lingo. Okay. Now this 10001. What am I doing here? This is how I used to do things, I think, before I made it better. Yeah, forget about that. This is how I used to do things. And what I'm actually doing there is thinking in terms of like a modified Phinary base, the golden ratio base. It's sort of a complicated story. Yeah, I'm sorry. Maybe I'll talk about. I sort of talk about that in the video that I haven't published yet. So sorry, it's a bit disorganized, but I do. So the thing is, like, I've been doing all this math since early May, and so I'm real busy with the math, and I don't really have time. Instead of making videos about it, I tend to work on the math. Right? I usually prioritize doing math work over making a video about it. So that's why there haven't been many videos or live streams or anything for since March. March is when I started focusing on math, and then early May is when I started focusing on this open problem, or there's two open problems. So there's more to talk about. Yeah. So I'll just say, if you play around with the Lucas representation, so there's sort of a, do I have a pen? No. Okay, so there's a very crucial identity with the golden ratio, which is that, so phi plus 1 is equal to phi squared. That's one of them. There's a second crucial identity, which is that phi minus 1 over phi is equal to 1. So phi minus 1 over phi is equal to 1. And so, because that is equal to 1, you can put parentheses around it to put it to the nth power. You can take powers of that, and it'll always be equal to 1. So in parentheses, you have phi minus 1 over phi. I know it's hard, it's really hard to follow math when somebody's talking, so maybe just write this down. Phi minus 1 over phi in parentheses, and then to the nth power. That will always equal 1. And so that's a binomial expression. You can start writing out all these things. And then it's always equal to 1. And what that gives you, it actually, if you dig into the details there, you start seeing the Lucas numbers pop up everywhere. So this Lucas representation ends up being sort of related to, it's related to like a modified finary base. That the modified finary base that I'm talking about is where, so you have the ones place, the phi place, the phi squared, phi cubed, and so on, dot, dot, dot. And then on the other side of the decimal, you have an alternating. So it goes like, I think it goes minus 1 over phi, positive 1 over phi squared, minus 1 over phi cubed, positive 1 over phi to the fourth. Now that's a little weird, but if you do that, then you get these nice, it's really nice to write integers, and it's intimately connected with the Lucas base and all this stuff. So maybe I'll get a whiteboard, or change how I'm doing this. Maybe I'll write stuff on the computer. I don't know, because just sitting here talking is probably not the best format for explaining these math things. But because I've been focusing on this stuff. So I've been focusing on Fibonacci and golden ratio stuff since March. Basically, the same time that I stopped doing many live streams, I've been doing math instead. And so what is that? We're almost at like 5 months of math. And so there's a ton of stuff to talk about that I think is interesting. The reason I think this stuff is important is you can get, I'll explain this as quickly as I can. You can get the golden ratio just by looking at a pentagon. The diagonals of the pentagon, so if the sides of a pentagon are of length 1, then the ratio of the diagonals to, because the diagonals are longer, the diagonals will be of length phi, length golden ratio. So you get the golden ratio immediately just from a trivial study of a pentagon. Therefore, when you have the dodecahedron, which is a regular solid with 12 pentagons as faces, you have the golden ratio just flying around all over the place. Even the diagonals that go through that solid are related to the golden ratio. I forget exactly. It might be phi squared, which is the same as phi plus 1, etc. I forget exactly, but anyway. And then, of course, the diagonals of the pentagons on the outside, all of that, there's the golden ratio just flying around all over the place. The icosahedron is also intimately related to that. And the icosahedron and the dodecahedron are part of what I'll call type E symmetry. If you want something more precise, because that's sort of vague, if you want to be precise about it, they're connected with type E Dinkin diagrams, which are connected with the special Lie groups or the exceptional Lie groups. And all of this is connected to physics, to particle physics, to octonionic unification physics and all this stuff. You can look at John Baez. He's a mathematician. He's actually the cousin of Joan Baez, the singer. And he has a blog post out there. It's called, I think it's called like the icosahedron and E8. So there's all this talk about E8 unification physics. That is I think E8 is it's the most complicated exceptional Lie group / Lie algebra. It's the most complicated example of this type E symmetry. I call it type E symmetry, but if you want to be technical, it's like Dinkin diagrams of type E and all this stuff. Or you just talk about exceptional Lie groups, exceptional Lie algebras, etc. But anyway, yeah, John Baez has a good blog post on that, the icosahedron and E8, something like that in the title. And then now he's kind of luring you in a bit, because it's actually not exactly the icosahedron so much as it's the four-dimensional analog of the icosahedron, which is this, that would be the 120 cell, I believe. So in 3 dimensions, there's 5 regular solids. There's the cube, octahedron, tetrahedron, dodecahedron, icosahedron. Okay, and those are the Platonic solids. If you go to higher dimensions, for the tetrahedron, you can have any higher dimensional analog of it. It's fairly straightforward to come up with. Those are called n simplices. And then that's just the name that they choose for that. They could have called them n-dimensional tetrahedra, or the n tetrahedra or something, but they chose to call it n simplices. For the cube, you have higher dimensional analogs, which are for 4 dimensions. They call it the tesseract. I think it was sci-fi writers that started calling it the tesseract. You could call it the hypercube, I think is good enough, or if you want to be specific, the 4-dimensional hypercube, because you can have an n-dimensional hypercube. So in general, the n-dimensional case, for the analog for the square or the cube, that's going to be the n-dimensional hypercube. So we have n simplices, n-dimensional hypercube. I'm fine with somebody saying an n octahedron, but technically, what is it called? A cross polytope or something? There's some name, I always forget it, for the octahedron. By the way, I figure if you're this far in the video, you're interested in this stuff. If you want to study the groups, these symmetries are described by groups in math. And if you want to study the group of the cube, you don't search for the cube group or something. It's called the octahedral group, because the octahedron and the cube have the same symmetries, basically. They describe the same symmetries. They're duals. We call them Poincare duals of each other. Okay. Now, so for those 3, they have these infinite n-dimensional families of symmetries, okay? N-dimensional analogs and so forth. But for the dodecahedron and the icosahedron, now I don't often think about the 2-dimensional case, okay? I mean, for the hypercube, the 2-dimensional case is the square. For the tetrahedron, the 2-dimensional case is a triangle, and so on. But anyway, I guess for the dodecahedron, 2-dimensional case is the pentagon. But anyway, I tend to just think about the higher dimensional cases. So some people, I think, will say that the dodecahedron and the icosahedron have 4-dimensional analogs. Now, I think I've come across people who object to that. I don't really care, because it's semantics, whether you want to call it the 4-dimensional analog or not. There's reasons in both directions. Now the special thing, something very special happens in 4 dimensions. There's a few ways I could try to explain this. But anyway, there's a special shape called the 24 cell. 24 cell. Some people call it a hyperdiamond. So that happens only in 4 dimensions. And why it happens in 4 dimensions has to do with, well, I could try to explain that, but I'm not prepared to, I'm sorry. I guess stay tuned for another video, or leave a comment asking for that video if you want. If you want to hear me explain why 4 dimensions and 4 dimensions only has a special regular shape inside of it. But it does. Very special in 4 dimensions. Now that shape, the 24 cell itself, fits inside either the 120 cell, so the 4-dimensional analogs of the dodecahedron and the icosahedron are we call them the 120 cell and the 600 cell. So I believe the 600 cell is the analog of the icosahedron, if I remember correctly. The reason is they're not called faces anymore. They're on the edges, on the outside, the exterior of the shape, you have full volumes, full solids. And so we call these cells. And so the 600 cell, I'm pretty sure, has 600 tetrahedra on the outside. So just like the icosahedron has triangles on the outside, on the exterior, on the boundary of the shape, the 600 cell, unless I'm making some silly mistake, is on the outside exterior of the shape in 4 dimensions. It has these tetrahedra, 600 tetrahedra on the outside. Okay, so, but one of these or both, these higher dimensional analogs, have inside of them, nicely embedded, the 24 cell. It's a bit similar to how in the dodecahedron, you naturally have these 5 embeddings of cubes inside of it. Okay. And then for the dodecahedron and the icosahedron, you do not have higher dimensional analogs after 4. Now some people, yeah, I'll call them analogs, but I think it is smart to view them as being special in their own right. And what does the word analog? That's not that doesn't give you any rigorous or technical thing to look at. You're just saying, oh, this one thing is like this other thing. But I'd say they are special. The 4-dimensional ones here are special. The 120 cell and the 600 cell. They are special because of the way that this special 24 cell fits into the picture there. Okay, now that's all hard to imagine because it's in 4 dimensions. Obviously, it's hard to imagine. But anyway, people look at these things. There's things that you can do to investigate it. It's all interesting, and somehow that stuff is connected with mathematical physics. That might be surprising. However, we have 3 dimensions of space, 1 of time, and we know that there's relativity. So we're talking about, we think in terms of a space-time manifold, okay? Which has, I guess, I'll say 4 degrees of freedom. So it would make sense that there should be maybe a connection there between 4-dimensional symmetries. I don't think we should be surprised, right? We live in 4 dimensions in a sense, not 3. There's 3 of space and there's 1 of time. And so we should not be surprised to find that certain 4-dimensional symmetries play an important role in physics. So anyway, blah, blah, blah. So it's my personal belief that when the next revolution in physics happens, and we understand that, I mean, it's whatever it is, it's gonna, I believe very strongly that it will unify gravity and quantum physics. And so, and I think most physicists agree with that, believe that. And so somehow this story, the quantum physics story of all of these symmetries of particles, has to be intimately connected or somehow married together with this story of gravity, where you have nonlinear sort of, I guess, transformations. I think of it as like this, well, squishing and squeezing of space-time, right? That's what Einstein's gravity is really all about, basically. It's about curvature of space-time, curved space-time manifolds. And, a big thing is I don't think you have inherent twisting in these manifolds. What you do have, you can have a rotating coordinate frame, which is, I believe that's the Kerr metric, but I don't think you have any intrinsic twisting. And I think I'm guessing that's a motivation for twistor theory, which is Roger Penrose's theory. And also maybe there's something called Einstein-Cartan theory. Einstein's gravity does not, to my knowledge, does not have a lot of inherent twisting. Maybe I'm just, kind of wrong about that. But I don't know, because I think they have a lot of trouble. I don't think they've figured out how to have two black holes in Einstein's framework, if I'm not mistaken. I'm pretty sure they don't have three black holes. You can kind of call that, you could maybe call that sort of the, Einstein's three-body problem or something like that. I don't think they even have it for two. But anyway, I'm getting kind of speculative and at the edge of my understanding and all that. But yeah, if you're interested in more, I recommend John Baez's blog post about, he calls it the icosahedron, but he's really pulling a switcheroo on you, because he really is talking about probably the 600 cell, the symmetries of the 600 cell, and how it's connected to mathematical physics. So what that means is, mathematical physics is not only physics, it's kind of all our attempts to use math to try to explain physics. So string theory counts as mathematical physics, but as far as we know, it's not physics proper because we don't have any evidence of string theory. Does that make sense? Anyway, and so the stuff with octonions is this sort of competitor to string theory, very interested in. And so this, what I'll call type E symmetry, plays an important role, which motivated my deep studies into the dodecahedron and so on. I used to do these Blender streams where I'd use Blender, the 3D modeling software, and I'd be playing around with icosahedron, dodecahedron, sort of studying it. And that was really good because I corrected, sometimes I corrected important misconceptions that I had. Sometimes I realized, discovered new things. So that helped me a lot. I was also figuring out how to programmatically create a dodecahedron, icosahedron, programmatically with Blender, which was useful. Anyway, and those are, when you do that kind of stuff, it's very closely linked with a neat algorithm for even and odd permutations. It's really deep because permutations are really foundational for much of mathematics, because in group theory, you have this theorem. Is it Lagrange's theorem? I forget. Where every group is a subgroup of a symmetric group, which means that every group, so every symmetry that they find in finite group theory, so every finite symmetry, is a part of some permutation structure, essentially. If you take, so if you were, say you're a kid and you discovered permutations and you found them interesting and you were playing around with them, you might find little interesting structures inside of this study of permutations. And if you made it all the way up to permutations of 120 objects, you could find inside of there the symmetries of the dodecahedron and the icosahedron. Isn't that weird? Imagine being a kid, being some little genius, and you are obsessed with permutations and like these hidden structures inside of them. I mean, given n objects, all the permutations of those objects, if you think that, why is there neat structure inside of there? Well, you can boil it down to the generators. I don't want to get into it. Look up about the minimal generating set of a group, that kind of stuff. There's a bunch of stuff. And so once you got to 120, suddenly, boom, you have, within that, you have the alternating group of order 5, which is the same group as the symmetries of the icosahedron or the dodecahedron. So permutations have this really fundamental rule. All this stuff is sort of connected. Yeah, I've rambled on enough here. Leave a like if you got this far, just as a little thumbs up for yourself, okay? If you want to. If you don't want to, if you feel like a dislike, you can do that too. Hope you have a great day. Bye.